I am so jazzed that I get to be with you today and that technology enables me to be in two places at once, literally teaching the class that I'm teaching right now and also being here to talk about active learning with all of you and to share some stories that I know Callie has expounded upon at this point. But I want to talk specifically about the fact that engaging students actively in their learning during the traditional lecture period often entails taking a certain amount of the content outside of the classroom. That is, we sometimes refer to this as flipping your class or making it an upside down class. There's been a lot of discussion about how to reference that, though I think the term flipping has certainly become fairly popular. And just this morning, I was delving into the literature a little bit about the flipped classroom and found an article in the International Journal of Teaching and Learning in Higher Education that references the flipped classroom. And I liked the quotes. One of the quotes that they used, they said, "The flipped classroom represents a student-centered method of fostering academic involvement that is recognized as a positive contributor to student success." Anytime you put student-centered and student success like twice in a sentence, I'm so jazzed. So let me just take a moment to say a couple of things about the way in which I like to use the flipped lecture. That is, I believe that not only does this allow you to take content outside of the classroom, freeing up the classroom period to do lots of active student engaged exercises, but it also enables you to do better than you could have done by lecturing in the classroom. For example, it allows you to take students to a remote location on a field trip with your content presentation, or it allows you in a lecture-based class to take them into the lab. A good example of this is the biochemistry course that we teach in our department for non-majors. This is the MOLB 3610, one of my favorite classes to teach, but it is a lecture-based class only. It has no lab component. So using a flipped classroom enables me to add a lab component. So the two videos that I'm about to show you, the first one is taking students on a field trip to talk about acid-base reactions, acid-base chemistry as an introductory portion of our biochemistry class. And then the second clip that I want to show is where I'm taking them into the lab. So showing that we can use these pre-watched videos, right? The students watch these before they come to class in theory or outside of their typical engagement to take them to places that maybe they wouldn't have otherwise gotten to go, even if we had lectured in the classroom. I am so jazzed to be joining you today from a ranch outside of a place called Cedar Edge. It's on the mesa near Grand Junction, and I'm doing a little skiing here, but I happen to be staying at a vacation rental that is actually a ranch. And so I've got in my backdrop the horses here, and also what's really cool about this place is that it happens to be on an alkaline flat. So I just talked to the rancher here, and he talked about some of the difficulties that he has with ranching on this alkaline soil. So alkaline meaning basic, and so we've got a lot of basic salts in the soil in this area. And I actually tried right before I came out to brew some tea that would have a natural pH indicator in the tea, and it's actually got acai and blueberry and pomegranate, and it's got a natural pH indicator. So I brought that with me too to see if we can see the effects of the alkaline soil on that pH indicator. So in this moment, we're transitioning into more coverage on acids and bases and looking at eventually we're going to turn our conversation away from strong acids to weak acids, and we're going to be looking at the Henderson-Hasselbalch equation, pKa and Ka values, and looking at eventually at natural buffers, that is buffers within the body that are things ranging from the natural buffering that comes from amino acids all the way to the bicarbonate buffering system, perhaps the most famous of all of the natural buffering systems, and incredibly pertinent to the equestrian world. So those of you who are horse lovers, but also those of you who are yourselves elite athletes, much like horses that are elite athletes, using a bicarbonate milkshake is a common performance enhancer within the world of the equestrian world. And so I want to read to you actually from an article about the bicarbonate buffering system and talk a little bit about that. So it's in the Veterinary Topics article, and it says milkshakes leave a bad taste. And at every level of racing, so much time and money are invested in each horse that trainers and owners want to find the extra edge that will help give even the most astutely trained and conditioned athlete to be more competitive. So manipulating timing of feeds, feeding, supplements can alter physical performance. One such controversial substance that has been actively administered to racehorses since approximately 1989 in an effort to enhance performance is sodium bicarbonate. Commonly known as baking soda, a milkshake is a quote colloquial term used to describe a combination of approximately 500 grams of sodium bicarbonate, glucose, and often other additives. These substances reduce acidic conditions within actively contracting muscle cells, and the milkshakes are used as buffers. So our conversation will be turning towards the latter portions of our coverage to buffering systems. So let's take a minute to see if we can't get our natural pH indicator to register this alkaline soil. So I'm going to try to move things around so you guys can kind of see the white alkaline flat in this area. In fact, you can see all around the alkalinity of the soil. So we're going to see if we can get our natural buffer to work here, our natural pH indicator. There are a lot of natural buffers too out there. I'm going to grab just a little bit of this alkaline soil. So we've got here's our natural pH indicator. Here's our very alkaline soil. You can see that there. Oh yeah. So we're getting an interesting color change as we see as we see the reaction taking place, and we recognize that this is changing from a very purpley color to an almost, it's getting in places yellowy green color. So nice natural pH indicator there in the pomegranate blueberry acai tea. Awesome. As I was walking back to the house, the pH indicator started to turn even more of a greenish, almost blue color. So I wanted to take a moment to show you how that reaction had continued even as I was walking back. And I also began to synthesize as I was headed to the house this idea of putting these two concepts together. So what about horses that naturally, such as the ones that were in the backdrop of that clip, what about those horses that do live in natural conditions where the soil is alkaline and they're eating hay that's grown in alkaline soil? And I started to wonder about natural performance enhancement based upon a diet rich in alkaline hay and alkaline soil, and I thought this might be something we add to our extra credit discussion on bicarbonate buffers that is natural alkaline soil such as we saw in this environment. So cool! Let's get a little bit closer view of this dialysis tubing. The brand that we're using in this case is Spectrapore, and what's really important is to look on the side of the box to make sure that you're getting the desired molecular weight cutoff. So when you look up close there, you can see that the molecular weight cutoff for this particular dialysis tubing is between 12 and 14,000 molecular weight units, often termed Daltons in the world of biochemistry. So 12 to 14,000 Daltons will be retained within the dialysis tubing, whereas anything smaller than that is going to pass right through. So let's actually go ahead and get a feel for what this is like in terms of pliability and before it's put into water, how does it feel? So you might be able to kind of hear this if I just pick up a little bit of this tubing. You can check this out and notice that it's a little bit crispy before it goes into water, not very pliable. However, I have some that's been sitting in water for a while soaking, and we'll pull that over. And what you notice about the tubing after it's been sitting in water is that it becomes really pliable. And I'll see if I can pull this out of here. Yeah, and you can see now it really is a lot more like sausage casing. It really becomes a lot easier to work with. And now you can pull it open and you can actually put whatever solution you want to put into it and allow it to dialyze. Of course, that means that you have to hold that solution in there. So I have some dialysis clips that are used for that. And we'll pull some of those out. And I'm going to go ahead and put a clip on the end here, and that'll actually keep whatever liquid is in here from coming out. I'll hold on to that. Sometimes you'll even put a knot in the end of the tubing as well. You can, if you really are hard up for money, you can just use knots. You put several knots in there and that'll work. So then we'll add our liquid in here containing the protein. And today I'm going to give a try to something kind of exciting. There's a protein that is very, very commonly worked with in the lab called albumin, and bovine serum albumin is one of the very common ones. So we're going to actually put a mixture of albumin into the dialysis tubing, but we're not going to stop there because we want to make this visual. So we're going to put some dye in with the albumin, and since albumin is actually a negatively charged or anionic protein, we're going to put in a positively charged dye and hope that that dye will color the negatively charged protein. And we're not going to stop there. We're going to add another dye, a Congo red dye, that is also negatively charged and hope that the protein repels that. So we're going to hope that the protein will retain the blue dye, repel the red dye, and that as we dialyze the solution, we're going to see that the red dye will come out because it's low molecular weight, and that the blue dye, because it binds to the high molecular weight protein, will be retained in the dialysis tubing. So we're going to do this cooking show style, and I'll be back with you in just a minute.
Okay, so to begin with, I'm adding the cationic or positively charged dye called methylene blue to the protein, and we're hoping that the negatively charged protein will bind to this positively charged dye. So in the Falcon tube, you can see there's BSA, bovine serum albumin, the negatively charged protein. I'm adding in the positively charged dye, and I'm going to mix this quite a bit, and I'm going to allow it to sit for a while that positively charged dye binds to the surface of the anionic protein. Now, after allowing that to sit for about 10 minutes, I'm adding the negatively charged Congo red dye. I'm hoping that this negatively charged dye will be repelled by the negatively charged surface of the protein. Now, it's important to note that I did add more of the negatively charged dye than did I the positively charged dye. This is important because in case the two dyes interact with one another just a little bit, there should still be an overwhelming amount of negatively charged dye interacting with the negative protein, and hopefully excluding that negatively charged dye from the dialysis tubing. Now here you can see me adding the protein solution into the dialysis tubing, which very much looks like sausage casing at this point as I work the bubbles out. To the top portion of the tubing, I'm adding a second dialysis clamp so that we can set this to dialyze in a buffer solution at a physiological pH, set the stir bar in motion, and we hope now that that red colored Congo red dye will dialyze away and that the blue dye will stay within the dialysis tubing.
Awesome. So FYI, for those of you who were curious, that experiment did not work. It turns out that the two dyes form a pretty strong precipitate with one another. So the cool thing was that the students got to do a lot of troubleshooting as part of an online discussion that addressed some of the issues with troubleshooting in the laboratory, which is something you wouldn't get generally in a non-lab course. So with that being said, I know that there are probably many of you out there, I know there are many of you out there that rock my world, and that many of you have used some sort of flipped classroom approach, or maybe you've used vodcasts or podcasts to in some way augment your teaching. So I'm going to turn things back over to Callie, and you can poll in while she's getting all set to go. And if you just send a text message to UWYO, text UWYO in your text message, send your text message to 37607 and tell us how you've used vodcasts, podcasts, or flipped lab approaches to augment your classes. Awesome. Thanks for letting me come.